Everyone to my channel. Today we will see lecture 5 from our DSA playlist, and today we will be learning about quickshort algorithm. Quickshort algorithm is a very famous algorithm used for sorting arrays. In quickshort algorithm, what do we do? First of all, we choose a pivot and we then place our pivot in its correct rightful position. And how do we do that? Suppose first in the first step, what we do? We choose a pivot and then we place the pivot in its correct position. And what correct position means? It means that all the elements that is smaller than all the elements that is smaller than the pivot would be placed at the left side of the pivot. All the elements that are smaller than pivot are placed on the left side of pivot, and all the elements that are larger than pivot are placed at the right of the pivot. All elements larger than pivot are placed at the right side of pivot. This is basically how it works. First of all, we choose a pivot and then we place the pivot in its correct position. And what by that what it means that all the elements that are smaller than the pivot are placed at the left side of the pivot, and all the elements that are larger than the pivot are placed at the right side of the pivot. And we have to do this for one particular case, and all the race cases are handled by recursion. We just need to consider one case and all the race cases will be handled by recursion. What it means that it means that we will do it for only one element. We will select one element as our pivot, and we will place the pivot in such a way that all the elements in its left side are smaller and all the elements in its right side are larger than the pivot. And then all the other elements will be also considered in pivot, and the same process will be repeated through the help of recursion. Okay. Now, first of all, let us understand this with the help of an example. Let's take an example. And example, I will take an array. Let's say you can consider anything, an array or a vector. Let's suppose this is our particular array. Now, which element should we consider the pivot at first? There are three ways of considering the pivot. You can either consider the first element as a pivot, you can consider the last element as a pivot, or you can also consider the middle element as your pivot, or the median element or the middle element as a pivot. You can consider any of the following. In this particular example, I will be considering the first element as a pivot. In this particular example, I will be considering the first element as my pivot, but you can and if you consider the median element or the last element as pivot, then there will be a little bit difference in the logic of the programming. But in my case, I will be considering the first element as pivot. Now, we will also take two another pointers. One is a starting pointer, start index. We'll be marking at our start index, and another will be marking at our end index. Okay. We have taken two pointers, one as a start index and another as an end index. Now, first of all, our pivot is pointing at the first element. Our start is also pointing towards the pivot, and our end pointer is pointing towards the end index of the array. Okay. Let's give us indexing 0, 1, 2, 3, 4, 5, 6, and 7. So our ending is pointing towards 7, and our pivot and start are ending towards the 0th index. Now, to begin with the procedure, what we do first of all is that whether our start index or our array or our element at start index is less than is equal to pivot or not. Here we use less than is equal to for if there are, let's say there are two elements with the same value. As you can see here, the elements at index 3 and elements at index 7 both are having the same value 2. Both are having the same value 2. So that's why we are using less than is equal to. Okay. I hope you got it clear why we are using less than is equal to. Now, if our start is less than the pivot, then what do we do? If our start is less than or is equal to our pivot, we just simply increment our start plus plus. We just simply increment our start by 1, and we do it in a loop, so it will keep on incrementing. So let us check. Is 5, just a minute, is 5 is less than is equal to 5? Yes, so increment our start. Our start is pointing right here right now. Is minus 1 less than is equal to 5? Yes, so increment our start again. Is 7 less than is equal to 5? No, then don't increment our start, don't do anything right that place. And do what? Check another condition from n side. Check another condition from the n side. What to check? If ARR at n index is greater than pivot, do what? End minus minus. Decrement our end by 1 index and also do it in a loop. Now our end is kindly pointing at 2, so is 2 smaller, is 2 greater than 5? No, then stop there. And do what? Do what? Swap their position. Swap the position of start and end index. Swap the position of start and end. Swap the position of start and end index. Okay, just swap these two. And also before swapping, also check that if our start is less than n, means the index of start should be lesser than the index of n, then only perform this swap. Okay, so if we perform the swap, what happens? The position will be replaced. 2 will come here and 7 will go there. 2, 9, 3, minus 6 and 7. This is what forms after swapping. And our start is still pointing here and our end is still pointing here. We have just swapped the elements and then perform this operation again. Perform this operation again. Check if our start is less than is equal to pivot. Yes, 2 is less than is equal to 5. Start get incremented. Again, is 2 less than is equal to 5? No. Sorry, is 2 less than is equal to 5? Yes. Then again increment our start, and now our standing is pointing to 9. Is 9 less than is equal to 5? No, 9 is not less than is equal to 5. So don't increment the start. C for end index. Is 7 greater than 5? Yes, 7 is greater than 5. So decrement our end. End is pointing here. Is minus 6 greater than 5? No, minus 6 is not greater than 5. So stop there. And again perform the swap after checking that start is smaller than end or not. Yes, start is smaller than end. Then perform the swap again. So after swapping, what does becomes our array? 2, 2, 7. Yeah, minus 6 will come here, and 9 will go here. Now this is what forms of our array, and our start is pointing here, and our end is pointing right here. Now again check, is minus 6 less than 5? Yes, minus 6 is less than 5, so start is pointing here. Is 3 smaller than equal to minus 5? Yes, 3 is smaller than equal to minus 5, so our start is pointing now towards the end. Right, start is pointing to 9. Is 9 smaller than equal to 5? No, 9 is not smaller than equal to 5, so our start stops there. And check if now end for the end. Is 9 is greater than 5? Yes, 9 is greater than 5. So 9 is pointing to here right there. End is pointing to here right now. Is 3 greater than 5? No, 3 is not greater than 5, so end stops there. And now this is the current indexing of our array. Where start is pointing to here right now. 9. And both have stopped. Now, tell me, do we swap the elements? No, we don't perform any swap, because as you can see, our start has overlapped our end index. Means our start has gone beyond our end index. So at this step, we don't swap between the start and the end index. Instead, what we do, we swap, but we perform the swap between the pivot element. We swap our pivot element with our end index element. ARR of end. We perform the swap between the pivot and the end. We perform the swap between the pivot and the end. That is, as you can remember, our pivot was always pointing towards the first index. Our pivot was always pointing towards our first index. As you can see here, our pivot was always pointing towards the first index. Now we just simply swap our pivot with our end index. We swap our pivot with our end index, and what does it give us? 3 minus 1, 2, 2 minus 6, 5 swapped, 9 and 7. And after the swapping, you can check that the elements that you have considered the pivot, it's now placed in its correct position. That is 5. All the elements to the right of 5 are all the elements that are right of 5 are greater than 5. All the elements that are present at the right of 5 are greater than 5. All the elements that are right of 5 are greater than 5 on the pivot, and all the elements that are at the left of 5 are smaller than 5. All the elements that are left of 5 are smaller than 5. Okay, and here it is, guys. Our partition function, this particular function where we're performing the loop, has been completed, and it will be another command of while loop that while start is less than n, we will keep on performing this, and up to here, and after that we perform the final swap. So this particular function can be said as our partition function. And this function will be called recursively through our quicksort function. This function needs to be called recursively, and in the end, we will return the end index of our end index. We will return the end index of the array, where the end is currently located right now. We will return that. Let's say we will we will return the location of our pivot, or return the location of the end. We will return the location of our end, and after we have done that, the rest of the test cases or the rest of the cases would be done through recursion. That means what? Up till here, starting from start to end minus 1, and from here to n plus 1 till the last the size of the array. Till the size of the array, we will give this 2 portion to our recursion function, and our recursion will again perform this partition function on this right side of the array and on the left side of the array, and that's how our whole array would become sorted. The recursion will handle all of the race cases. One case I have shown you, and all the race cases recursion will handle, and at the end our array will become sorted something like this. At the end, our final array will become something like this. It will become absolutely sorted, in which recursion will take all the elements as pivot, and it will place the pivot in its right position. Let me show you the pseudocode for an example, and also the detailed code will be present in the description of this video. You can do consider checking it out, and it will be very helpful to you. So first of all, let me write you the recursive function. As I have already shown you, the partition function, in where we perform we place our pivot in its correct position. Let me show you the recursion function as well. Here we can take a vector or an int, anything, and we will take it by reference. We'll take a lower bound and we'll take an upper bound. We'll take a lower bound and an upper bound. And if at any given condition, this is the base case of our recursion function, if our lower bound is greater than the upper bound, then return at that particular position, because our array has been sorted. Okay, now take another pointer as location, and what this location will give us is the end index. Location will give us the end index from the partition function. Lower bound and upper bound. What this location holds is this location holds nothing else but this return of the end index. As the end index has been written, so it holds that. And later what we will do, later again call the quickshort function recursively, and it will run from lower bound to location -1 for this portion of the array, for this portion, and another quickshort function will be also be there, which will run from location +1 to upper bound. That means this portion of the array it will run plus quickshort function. Okay, now this is for the recursive function, and now again I am writing the partition function for you. So in partition function, we are taking the partition function as int, as we also need to return the end index. That's why again take the vector by reference. Again take the vector by reference. Take the lower bound, take the upper bound, take the upper and lower bound. Now consider the pivot, and as I have shown you, we are considering pivot as the first element. We are considering pivot as the first element, so that is the lower bound of the array. And we are considering again two more elements, that is the start. Start is initially pointing to lower bound, and end index is initially pointing towards the upper bound of the array. Okay, now we do our actual programming here, actual logic. So while start is less than end, the whole loop will be continuing while start is less than end. Now in between that, while start is less than is equal to what? Array of pivot. Excuse me, sorry. Let me do it right here. If our array of start index, if at the start is smaller than the array of pivot, means the pivot element. Let's for simplicity, let's say like this: if while the start is less than the pivot, do what? Do a start plus plus, increment the start by 1. In the while loop, start another while loop. Within that while loop, check that if our array of end or the end index or the end is greater than pivot, sorry, is greater than pivot, do what? Do an end minus max. Decrement our end by 1. And at the end, check if our our array of means that the start is you can just simply do like this. We don't need to complicate things. We can check what? We can just simply check that if our start has not overlap our end, or our start is smaller than our end by indexing. I mean to say the index. The index of start index and the end index are not overlapped. Then do what? Then perform the swap of ARR start to ARR end, which means this swap, this particular swap that we have been considering, this particular swap. Do this. Okay, now once that is finished and the main while loop has been closed, that means this particular while loop has been closed, do what? Perform the main swap, which perform this main swap of our ARR pivot element with what? ARR of end, with the end index. And by doing this, our pivot is being placed at its rightful position. And then do what? Then return the end index. Return the end index of the array and close this function. Close this function and return the end index. And by this swap, I mean to say that the final swap that places our pivot in its correct position. The final swap that we are performing. The final swap that we are performing places our pivot at its correct position. That's it, guys. That's it for the video. And here we return our end index, and through this end index we will again perform this particular quickshort function or this partition function from the left part of the array and to the right part of the array. That's it, guys. That's the whole logic behind the quickshort algorithm. And now I will tell you about the time complexity as well. The time complexity in case of worst case, is big of n square. For average case, the time complexity would be big of n log n. For average case, the time complexity will be big of n log n, and for the base case as well, also the time complexity will be big of n log n. And as for the space complexity, the space complexity is big of n. Why? Because it is the stack space. It is a auxiliary stack space that has been considered, while for the recursion stack space is being considered here. And if you liked our video, please make sure to subscribe to our channel and put a comment down below the video.
Eyes in the sky, gazing far into the night.